Thank you very much for having me a very good opportunity to give a talk in such a prestigious and very nice conference. And I'm going to talk about, as introduced, about integrated model of Rayleigh-Taylor and Richtmyer-Meshkov instabilities in inertial fusion plasmas. The talk contains, after introduction, I'm going to talk about a 1D dynamics, very simple one, and add perturbation as a Rayleigh-Taylor growth. And finally, I'm going to give some example of analysis of our previous implosion experiment. I wonder how it works. Doesn't work. It may be wrong.
Could be a battery issue. Possibly.
Sometimes it just doesn't work on Mac.
Oh.
So you might just have to click it.
So maybe like this.
Oh.
Yeah. Does this work?
Yeah. You can see the cursor. Even with the battery.
Okay. How ICF works. Initially, container, so-called capsule, that contains DT ice showing blue and DT gas in the center. And those capsules are irradiated by a strong laser or soft X-rays. And the outer part of the capsule is very heated up by this energy source. And then the heated material expands toward the vacuum. And as a result of expansion, as a reaction of that expansion, the rest part of the target is accelerated inward. That is an implosion. And finally, it will stop at some stage. And initially, iced DT becomes a main fuel with a density of 1,000 times liquid density, whereas the initially central gas part is adiabatically compressed and heated to a very high temperature that generate a DT reaction. And DT reaction produce many alphas, and those alpha has an electric charge so that it is absorbed in a central hot spark to increase the temperature again to generate further DT reaction, that is ignition. And once ignition takes place, the burn DT wave, DT burning wave, propagate from the inner surface of the compressed main fuel toward the outside to finally generate 100 times energy gain. And as everybody knows, Livermore made a ignition very recently, and congratulations to United States for such a ignition in humankind. But high gain is remained to be explored for future. So the largest obstacle to high gain is quenching of hot spark by hydrodynamic instabilities. The initial seed is simply target surface roughness plus a seeding of non-uniformity due to the laser irradiation non-uniformity. And those perturbation is amplified by Rayleigh-Taylor instability in the acceleration phase, and again amplified at the deceleration phase at the final stage. So at the end of the compression, this shows a 3D computer simulation showing the interface between the hot spark and main field. And you can see in the left-hand side, the spike is falling down into the hot spark, whereas the bubble is flowing up to the main field. And here is some stage after that. And since the surface area of bubble region is so big, so the thermal conduction easily cooling down of the temperature of the hot spark. That means quenching the ignition. So we have to control this Rayleigh-Taylor instability. So our goal is to develop an integrated model to find the high gain target design in a reasonable accuracy. So to do this, we have 4 steps. 1, 1D implosion dynamics, and 2, initial perturbation, that is target roughness and laser imprint, and 3, Rayleigh-Taylor growth, and finally hotspot eroded by Rayleigh-Taylor instability. Okay, acceleration. Target acceleration is well described by a simple equation of motion with mass aberration. This is simply momentum, and momentum change is caused by the force, that is the pressure times surface area. And pressure and mass aberration rate is very well known, which should proportional to the laser intensity to the 2/3 and laser intensity to the 1/3. And this model is surprisingly well predict the implosion dynamics. This is a comparison between the model and 1D simulation, as well as a comparison with many experiments. And 1D dynamics is almost perfectly predicted. And shock, the second point is when it becomes deceleration. And that timing is determined by the spherical shock first converge and collapsed at the center, and second shock hit the imploding shell. This determines the timing of the start of deceleration, and this is also analytically derived in many years ago. So we just take it to use to predict timing. and radius. And the third point is a main fuel deceleration phase. The deceleration phase dynamics is also well described by the equation of motion with little aberration. In this case, aberration doesn't matter. So the equation of motion, the mass is outside of the derivative. The point is, since the hot spark is adiabatically compressed, then the adiabaticity predict the pressure is proportional to the volume to the gamma. That means the radius to the -5th. And with this given condition, the solution is a very simple one. It's a quadrature relation between the radius and time. It is surprising that such a simple solution is very universal one. There is no exception if we give terminal velocity, which is determined by the pressure times volume divided by the mass. So there is only one unique curve in deceleration phase. So, okay, the perturbation. Surface perturbation is very accurately measured. And in this particular example, the surface roughness is 18 nanometer, very, very smooth one, with a very well-known power scaling. The initial imprint is a bit difficult. The initially perturbed laser produce pressure perturbation on the surface, and pressure perturbation also produce momentum perturbation along the vertical direction of the target. And this equation is a simple equation, but it is predictable to the surface roughness. You can see here the comparison between the model here. No, this is the simulation. Model here, and simulation here, and experiment here. So I think accuracy is good enough to use this model to predict the initial imprint. And furthermore, the modern ICF laser technology has a temporal smoothing. Temporal smoothing means, for example, if you look at the room light, the paper is illuminated very uniformly. There is no fluctuation. But if your eye has a picosecond resolution, it's a bunch of fluctuation due to the interference speckles. So the idea is to use a broadband laser to smooth out by quickly changing the speckle pattern on the target. So to simulate this situation, we simply used Young interferometry, but with two different laser color, so that this Young interference has moving with time. So you can see here the streak picture of this interference fringe. The fringe move some speed determined by the wavelength difference. So this is the comparison with the theoretical prediction and experiment. The agreement is not fantastic, but quite acceptable. So okay, let's use it. The third one, this is the most important and difficult part, the ablative Rayleigh-Taylor instability. If we know that the growth rate gamma, then we can easily calculate how much amplification is expected. But the problem was the gamma. Since the material the ablated material removed the perturbation away from the unstable surface. So the people can say that the ablative Rayleigh-Taylor instability is somehow reduced by a material ablation, but problem is how much. There are long history. Steve Bodnar, NRL, has initially proposed, okay, if a classical kg, growth rate root kg, if there is classical one, then the growth rate should be reduced by kVA. VA is ablation velocity or flow velocity across the unstable interface. The velocity to remove the perturbation away from the unstable surface. And Yang Takabe in our institute determined the coefficient for DT target. A coefficient in front of this ablation term, he found that is 3.5. And Young Betty said, no. Since ICF target does use CH capsule or beryllium, whatever, then there is X-ray transport. So the ablation surface structure is determined not only by the electron conduction, but also the X-ray transport. And he found this factor is 1.7. Okay. Let's compare with the experiment. And experiment shows that beta of 1.7 at least is in very good agreement in a short wavelength region. The longer one has another physics, so I don't want to say anything about this now. So the process is now to integrate the growth rate gamma with time. And very fortunately, the growth rate can be analytically integrated to be a simple form, root L and beta VA ablation velocity divided by implosion velocity, very simple form. And I1 and I2 are described like this. In the same way, the deceleration phase growth exponent, large gamma t, is also described in a very similar expression with a different integral, I3, I4. Those are also analytical function. So the final perturbation amplitude, Gauzy, L, is a sum of all three exponents, gamma arc, gamma feed through gamma deceleration. And if this amplitude exceeds the multimode saturation amplitude, SL, proposed by Stephen Hahn, he developed a theory to predict saturation amplitude if there are many modes, not a single mode. If there is a many mode with random phase, and some mode construct together to have real space amplitude, which becomes some fraction of wavelength, and then so he found saturation amplitude for multimode. So when amplitude Gaussian-T(S) is larger than the Hans saturation amplitude, then the Rayleigh-Taylor becomes nonlinear, and the Rayleigh-Taylor spike freely fall after Ts. So the spike amplitude Gaussian spike is initial amplitude plus double integral of gravity. It's just straightforward. So Rayleigh-Taylor spike freely fall, as I told you. That means that makes a straight line in the lab frame. So this is again trajectory of deceleration phase, and this trajectory is a falling line, and neutron yield or fusion reaction can only inside this straight line. That's a model, and this is the final conclusion. The data was very old one when I was 38. But I took that data and compared with the newly developed theory, and you can see here the agreement. That is a YOC. YOC is a yield over neutron yield divided by 1D predicted neutron yield. So YOC as a function of convergence ratio, and in lower convergence ratio, the YOC is around 0.1, and whereas in convergence ratio of 30 or so, that is almost 1,000. So the next step, this model should also be tested in Riff's recent and previous experiment that is to be continued. So in summary, an integrated model is developed that includes 1D implosion dynamics plus perturbation seeding followed by Rayleigh-Taylor growth, and 1D dynamics and yield degradation are well reproduced. And the model is used to predict high gain targets to cross Devil River, Valley of Death, and Darwin Sea towards carbon-free, limitless, sizable energy production. Thank you very much.
Thank you very much. Question, Suzanne?
One question and also a comment. Would you please go to these theoretical models?
Which one?
Earlier, like, I mean, Takabe, Betty, Nima.
Takabe.
Yeah, like, you know, all these pictures.
Okay.
Yeah, this one. I just would like to make a comment that most of these common models are actually empirical or semi-empirical models. They have been developed with a desire to adjust, like, you know, certain data. I will be discussing today the regress theory, which is coming from the conservation laws. Maybe it would be of interest to you and your colleagues to compare with. And associated question, you mentioned that you compare with data which were like 30 years old. But you know, if you have the data available, we will be happy, more than happy to compare with them, because experimental data are immortal. Whether they're 30 years old, 50 years old, or 100 years old, they are still the data.
Doesn't matter.
So if
Thank
the
you.
data are available, we will be
Thank
happy
you.
to compare with. And also to look at the some parameters. And if possible, on the other figure, when you show the growth rate depending on wavelengths, maybe a couple of slides ahead. Yeah, it's a number 13 slide, right? Absolutely. Yes, this one.
Yeah.
Some of the parameters, it's actually you see that there is a like non-monotone dependence on the wavelengths, right? So there is a maximum growth rate, so characteristic lambda, and also there is a sort of a cutoff, like you know, the critical growth rate. Have the dependence of these wavelengths, maximum growth rate or a critical growth rate on experimental parameters have been investigated in details in experiments, or at least monitored? Do you know how it depends on like?
You mean the
yeah, this one is
this reduction. This reduction
yes.
is obviously aberration.
Yeah, but I mean, do you have a table showing, like, you know, critical wavelength this, ablation velocity that? Because it may depend on some parameters, right?
Well, there is a zero growth rate if aberration.
Yeah.
And we believe this reduction is aberration. And we don't know this reduction in longer wavelength. We suspect in any Rayleigh-Taylor theory assumed the very uniform laser income. Every theory assumed the flat critical density region, but it doesn't actually.
It doesn't exist, yeah.
It should be deformed, and I think this reduction is due to the deformation of critical density layer. We made a simple model, but maybe discuss with you.
Yeah, I would be happy to send you. Would be delighted.
Yep. The Rayleigh-Taylor instability is an incompressible instability, but you're compressing your system. So if you compressed it much faster, if you had a much shorter laser pulse, then G would increase because you're doing it faster, but the Rayleigh-Taylor instability only goes like the square root of G. So could you make the laser go so fast that you outrun the Rayleigh-Taylor instability, and then you don't have to worry about it?
I'm not sure. Well, in general sense, the ICF target is compressible one. Otherwise, we can't compress.
Right, but can you compress it faster?
Yeah. But please, the inverse of growth rate is long enough.
No, actually, my question would be one sort of different, because when it's a shock given or shock plus ablation pressure, there is a superposition of motions. The uniform motion, like 1D motion, it can be supersonic and even hypersonic, but the growth of the interface perturbations, instability itself, it's a well subsonic, really compressive. So it's actually the superposition of motions.
James, go ahead.
Yes, there's an obstacle to driving it faster, which is a laser instability in the holoron, which generates, due to a turbulent kind of instability in the laser, it drives hot electrons, and they preheat, and they put the whole trajectory on a higher adiabat, and so they have, the only progress they've achieved is by not overdriving the laser. So you cannot solve the problem in that way.
Good, very good point. Yeah, I agree. The laser is usually coherent, And since the ICF need many laser beam, so multiple laser beam can interfere to generate an interference fringe that enhance ion acoustic wave, and that ion acoustic wave acts as a grating to diffract out the incident laser. That's a serious problem, and I don't know in future that problem can be solved. Maybe a very broadband laser can solve.
So for like the direct drive seems to be still, sorry. So the CBET, what you're mentioning is the CBET, is like still for the direct drive like an issue, but for like the indirect drive, in fact they use that to like a little bit shift and give more energy to like the inner beam compared to the outer beams. So they're playing in fact now with the CBET. It's very well understood, the CBET. There is not so much issues than the kinetic Raman scattering that have been just mentioned. Where like you start to like preheat like the fuel, and so I start to have like an asymmetric like combustions, ignitions. But yeah, so I think like for the CBET is pretty well understood. That's my consider. Yeah,
pretty well understood, but
no, but they play.
I'm not sure there is answer.
They play with that. They play with that now.
Yeah,
I can
okay.
prove it. What I understood from.
2% broadband is very difficult.
Yeah, I mean like
yes.
Rochester trying to like,
yeah. The only solution is probably OPA, pumping a coherent laser, and seed laser that should be broadband, that can be amplified in OPA. That's a solution.
Yeah, for IFE maybe there's like a lot of technology, even like the excimer laser.
Right. That's what you're right.
All right. Are there any questions from the virtual audience? Please unmute your microphone and speak out. Sounds like there's not. Maybe I just ask the final question about the gain. So you mentioned a gain of 100 in your first opening slide. What gain? Where does that number come from? What actual gain do you need? I mean, a minimal.
Minimum. Eta. The minimum gain, that is a zero generation reactor, that is eta, the driver efficiency times gain equal 1, right?
Yeah.
So the eta is typically 10% at most in laser. So 10 times 10 equal 1. So the minimum is gain of 10. But that is zero output reactor, so we need 100.
Yeah. Very good. So let's thank Professor Azechi again for a wonderful talk.
Thank you.